Thanks for all sticking around. I kind of expected the room to be half empty by now, but everyone seems to want to stay for the entire workshop. So first, before I get started, I'd like to mention my collaborators, the people I've worked with a lot on this. Argavan Safavi Naini. Okay. She's a graduate student at MIT that's been working at ITAMP with Hossein quite a bit, but I got to borrow her for this. And then Javier von Stetcher, who was at Gilla. And then Barbara Caprogrosso Sansone, who was an ITAMP postdoc, but now is at the University of Oklahoma. So Caprogrosso. I can't spell words. So, yes, just throwing me off my game here, Hossein. So I'm going to be talking about three-body interactions today and RF fields and couplings. And I was really glad to be following Chris, actually, because now that means I don't have to give a description of the Efimov effect and all the glorious, beautiful things that show up there. Now, there is a downside to following Chris when you're talking about universal three-body physics. It's kind of like the act that follows the Beatles or something like that. So, there's a lot of interesting work going on in Efimov physics and in universal three-body physics, and a lot of great things left to do. But one of the questions that I wanted to start answering and thinking about is, we have all this glorious universal three-body states available to us. Is there some way that we can start using them to produce new physics in a laboratory environment? Is it beyond just probing Efimov physics? Can we start using Efimov states to do something? So that's kind of the picture I have here. So I have three overall topics. I'm going to talk about kind of RF association of three-body states briefly, kind of more of a review of the state of the art on that. Then talk about how we can use these kind of RF coupling schemes to create a tunable three-body interaction on lattice sites. And finally, what the resulting phase diagram for the Bose-Hubbard model comes out, including these. All right. So moving right on to RF association. So this is really just a review of what's happened and kind of some ideas on how we can, push things forward. So Efimov physics, fairly well established now in experiments. You saw from Chris, there's a lot of experiments, a lot of groups out there seeing all sorts of new things. A lot of great work still going on with this universal short-range cutoffs and things. But one thing I was going to point out is most of the things that have been done so far in trying to probe Efimov physics or universal three-body physics happens at zero energy. It's all scattering properties, right? So we've seen these like three-body recombination resonances here and here. People have now seen the atom dimer scattering resonances and these Stuckelberg minima that have been seen, but it's all kind of at zero energy threshold. So you can kind of say maybe we've seen the zero energy spectrum, but that's not much of a spectrum. So the next question is, can we start seeing more of the Efimov state? Can we actually start probing and looking at the binding energy of these things? So there's some early things going on. So recently there have been some experiments in RF spectroscopy recently. I guess a couple of years ago. That's old hat in this world, I guess, now. So just to show a picture of what this RF association kind of process looks like. So for lithium-6, it's actually not purely Efimov physics. It's not three identical bosons interacting resonantly. It's three distinguishable fermions that can have a scattering length that can be tuned to fairly large numbers, but you can never have all three scattering lengths being the exact same and resonant at the same time. But this is kind of the overall energy diagram that you would expect to see from this system. So the experiment we imagine is we start with a two-component Fermi gas, a mixture of dimers and a single atom. And we want to flip the hyperfine state or the internal state of one of these to the third distinguishable one. And there's kind of three different things that we can probe here. We could go RF associate directly to the Efimov state, the three-body bound state, or we could kind of do a spectator particle flip where the dimer doesn't get changed around and the third particle just flips over, so sort of a single body process. Or really there's a third one where we can break up the dimer and flip a spin at the same time. Those are the three processes you can really see. And then there's actually another threshold that I'm showing in here that we're not really going to probe. And you go through and do the experiment. This is from Nakajima et al., a Tokyo group that has done this. And sure enough, this is exactly what they see. They see a nice little loss. And once they go to these three distinguishable particles, they can get very strong three-body losses. So they can look at the loss rates, or the number of atoms remaining, and see these kind of resonances. So they get one resonance that's a little bit lower here. That's the Efimov resonance. One very deep one that is just the single particle flip, and then one that's including the breakup. Right? And the thing that we're kind of concerned with is now this difference in energies. This is mapping out the Efimov energy. So here's some of the experiments that have done this. The first one, I should have probably mentioned this, was done in Selim's group in Heidelberg. That's this one here, where they started mapping out this Efimov binding energies, and they saw it was fit the universal theory very nicely. And then after that, the Tokyo group did the same experiment and found that it didn't fit the universal theory that nicely, but still, I think it's pretty close. And then more recently, in this kind of odd, like no-spin flip RF spectroscopy, kind of a wiggle spectroscopy method, group in Tel Aviv, Lev Kajkovich's group, has started mapping out the binding energies. And I don't really understand this process very well. It's kind of like using an RF wiggle to change the scattering length in non-adiabatic couplings. And I don't understand it well, but they claim that they've got this working very well. So moving on. So this is kind of the state of the art now. But one of the things that I can point out here is still we're dealing with things that are still very close to threshold. Right? All the lithium-6 experiments happened very near an atom dimer threshold. And the Israel group has all done things near this atom dimer threshold. And the reason that it has to go that way is because, these Efimov states, while they're large universal three-body states, they're really not that large. They're pretty small states. And if you want to do an RF association, right, you have to have decent Frank-Condon overlap, or you'll never get any formation of trimers. So when the states are near here, they have this very large kind of atom dimer type of wave function, where you have a dimer with a very weakly bound atom. So it's this huge kind of Feshbach-looking molecule, right, that has pretty good overlap with like either the three-body continuum, or in this case down here, the atom dimer continuum. Right? So we're still kind of limited to really near this atom dimer threshold. So is there a way that we can extend the regime in which RF spectroscopy can probe Efimov physics? So this is a quite simple idea, right? Why not just use a tight trap? Right? Put three particles in a tight trap. If I start, say, with three identical bosons and flip one spin, if we imagine that the scattering length between the blue and the red here is very large, you can get Efimov states attached to this excited threshold. Right? But the presence of this external trapping, right, limits the spatial extent of the original wave function and gives you fairly good overlap with the final state, which can help us. And in this picture, we have the bound state and an initial kind of near non-interacting three-particle state. So we can kind of think about this as a two-state system. Two-state system will have some Rabi frequency associated with it. So we can find out what that Rabi frequency is. And we can actually get that analytically. It's some polygamma functions and the like all over, but I'll show it just as the graph here. And here I'm showing the three-body Rabi frequency. I've assumed that the identical boson scattering length is 0 for this, and that the dissimilar scattering length has gone off to infinity. Right? And as a function of the energy of the Efimov trimer in the trap minus the non-interacting energy, we can map out this three-body Rabi frequency. And I should also point out the Rabi frequency here is kind of in the weak coupling limit. It's exactly equal to the one-body spin flip Rabi frequency times the Frank-Condon overlap, and then we get this nice little square root of 3, which is kind of a boson enhancement, identical bosons. And you can see that you can get all the way up to like 70% of the single particle Rabi frequency, which is significant, which might give us a new probe into mapping out Efimov state binding energies. And so just to make that a little bit more concrete, if we put in rubidium-85, say, or something like this, there's a van der Waals length of about 82. And I set the three-body cutoff that Chris had talked about to something about that. Doesn't exactly give the right 9.5 three-body parameter, but it gets pretty close. So we use that as an estimate. Now, with a 10 kilohertz isotropic trap, we can find that the binding energy of this state is about 2 trap units, 2 h bar omega, right? And the three-body Rabi frequency is about 60% of the single particle, which is significant. I mean, right away, in an optical lattice, 10 kilohertz shouldn't be too hard to achieve. Pretty reasonable number. So we should be able to, right away, see the bound Efimov states. I mean, it depends on what this dissimilar particle scattering length looks like, but shouldn't be too big of a problem. All right. So that was all I had to say about RF spectroscopy. So now we can have this way of coupling an Efimov state to a ground state fairly strongly. So can we start using it? So that's what I'm going to talk about here. And here I'm just kind of showing a schematic of that I'll show a little bit later of kind of 2, 3, and 4 body systems with an RF field coupling it. We're going to use the fact that these are different at different energies in the near future here. So going back to this idea of using this two-state system, we start out with a basically non-interacting identical 3 boson system, Efimov state, up above with a single dissimilar particle. We can turn on some RF field that's detuned from this transition a little bit. Right? And we can imagine that the ground state of this absorbs 1 photon, emits 1 photon, absorbs and emits and absorbs and emits, right? And turns into kind of a mixed ground state. We're just going to mix in a little bit of Efimov state character to this. And as a result of mixing that little bit of Efimov state for a red detuned system, we decrease the energy a tiny bit, which is nice. Now when we have 3 particles on a single site here, if we imagine this isotropic oscillator is actually a lattice site, when 3 particles are on site, we're pretty close, we have an RF field tuned pretty close to this Efimov state, and we can affect the energy just by changing the detuning or the Rabi frequency. So that's pretty neat. Another thing that I'm going to point out here is, well, if I can start affecting the energy of the 3-body state, what happens to the 2-body states or the 4-body states or the 5-body states and so on and so forth? So here's a figure of the binding energy of these different 2, 3, and 4-body states as a function of the scattering length, this boson distinguishable particle scattering length, in units of the oscillator length. So A goes to infinity is over here because it's 1 over A. This is the negative scattering length side, but we're still mostly concerned with the infinity. So the way you can see is the 3-body state is, about, for this particular case we're looking at, about 1 oscillator unit below the 2-body state. And the 4-body state actually drops off the map here and goes down to about 6 oscillator units down. So there's a fairly good gap here in the energies. So the 3-body state is fairly well isolated as well. So going back to this picture. So if we tune something fairly near this 3-body transition, right, well, we're pretty far tuned off from the 2-body transition and pretty far tuned away from the 4-body transition. So as a result, only 3-body occupation gets affected in any way. So since only 3-body occupation gets affected, and see I can now point to Hans Christoph's talk earlier, because he introduced the Bose-Hubbard model, and I don't have to do that either. It's excellent. Makes my life easier. Right? We can now imagine a new kind of Bose-Hubbard model. It looks like this. So we have this hopping terms, where it's just a hopping energy, and this ij goes over nearest neighbors, energy associated with 1 particle moving to a neighboring lattice site. And then we have this normal kind of mean field interaction, u n times n minus 1 over 2 behavior, which really is kind of the energy of 2 particles on the site. And now with this external field on, we have this additional 3-body interaction. But because the external field is tuned to only that 3-body transition energy, it only affects the 3-body states when 3 particles are on site. That's what this Kronecker delta is telling us. And so here's kind of a schematic of it. So one thing you want to know is, how big can we make this U3? Is it getting big enough to be useful in any way? All right, so you can do some quick kind of calculations, and we find U3 in units of the 2-body interaction. Here the 2-body interaction is about 1 kilohertz, fairly smallish, but still a doable number. And I'm using a single particle transition frequency of about 1.5 kilohertz, something that I think is very doable for an RF transition. I believe Selim, where's Selim? Oh, there, hiding behind Peter. You were doing about 10 kilohertz for your RF? Yeah? 1.5 is doable? Okay, see? So, and then I'm just showing here, this is kind of the lifetime or the width of the Efimov state, doing a quick semi-classical calculation, something about 0.6 to 0.1-ish oscillator units in this picture. So by changing the detuning to the red here, what's happening, you can see that we can get these 3-body energies of order, and attractive here, I'm going to focus on the attractive side, of order the 2-body energy. And that's kind of the fundamental energy scale that we care about in the Bose-Hubbard model. So we can get some fairly strong interactions, just to prove to you that this works. All right? So moving on, I'm moving way faster than I expected, so you're going to be out of here all kinds of early. Maybe I should just make some jokes or something for a little while.
Maybe I ask you a question. If you go back,
yeah.
If I would have 4 particles on a side,
Mm-hmm.
would I not have would I not expect to have 4 times U3?
You would, normally when you have a 3-body interaction, it's exactly kind of this. You'd expect this U3 n times n minus 1 times n minus 2 over 6. But here, if we go back to this kind of picture or to this picture, right, we find that because the 4-body state is detuned, not really anywhere near resonance with the 3-body, the RF field that we've put on here, it doesn't really see that field at all. The field is transparent to the 4-body state, and so it just sees the normal mean field energy and doesn't get affected by the 3-body or by this additional tuning. So really, we've selected out only the 3-body states or the 3-body occupation that gets pushed around at all by this external field. Everything else follows the normal mean field. So, I mean, you could, I mean, I guess some people have argued that you'd expect to see like something like a 3-body spectator system with a, you know, or a spectator. But because this 3-body state is so large in this oscillator state, the Efimov state is so large, you never have a spectator particle. It's always interacting with the Efimov state, and it gets pushed around. That's what this is showing. So here's the lowest 4-body state. And then you have another 4-body state that's up here, but it's still well separated from the 3-body state. And then actually there's another one up here and another one up here. But they're always separated. They're never a spectator system because this 3-body state is so large. And same with the 5-body, actually. There's a 5-body, what Chris had shown from Javier's work earlier. There's a 5-body state that's attached to this 3-body state as well, but it's way down here too, and a 6-body, a 7-body, and 8-body, but they're very well separated from the system. And also, again, because these Efimov states are so large, you never have kind of a 3-body with spectator type of system. It's always going to be pushed out of resonance with the RF system.
Sorry, I have a question
Oop.
too. You have actually an Outler-Toms doublet, right? But
Yes.
You're only showing one energy.
I'm only showing one energy. That's the one that I'm concerned with. In the really, this graph was maybe a bit of a misleading statement because we're not necessarily in the large detuning limit. But in the strong detuning limit, the energy that we're concerned with is the one where we only do fractional mixture of this extra state in the strongly detuned limit. And this is kind of just an initial calculation here that I put together like 3 days ago for this talk. But we've been playing around with parameters, and we think that in the strong detuning limit, we still should be able to get similar kind of numbers, U3 over U, about of order 1. So.
Like, it appears you could do, like, create a similar turn in different ways. Like, for example, you could just drive from the S band to the P band, let's say, of the optical lattice, and then use the 2-body detuning to single out the 3-body state, right? That would equally give you that term, and one can probably write down different, like a number of ways to that, you know? Like, is there something specific Efimov-ish about this, or something specific that you need, or why should I use this Efimov way that you propose?
Well, because we know where Efimov states are, and I can do the math analytically. So that's why I'd care about it. But, or semi-analytically. That's one reason. I don't know if there's any specific reason. Efimov states have become well studied in both now in rubidium and lithium and any number in cesium. It's all over they're all over the place. So we have a lot of systems that we know Efimov physics exists in. We can play around with it. So it's on a good reason maybe to use it in that way. I don't know really. I mean, I am a simple few-body physicist from Russian forest, I guess, to paraphrase George Shliapnikov. So this is kind of my early ventures into many-body physics. I was actually at some, you know, in the next slide or a few slides, you'll see that I did a Gutzweiler-Ansatz solution. I was really proud of myself for that. You know. Woo! So phase diagram. See? Gutzweiler-Ansatz. So we have our Bose-Hubbard model. We make the Gutzweiler-Ansatz where we assume our superfluid order parameter has this kind of form. We make a kind of homogeneous assumption where each site has the exact same sort of behavior for a variational kind of Ansatz wave function. Putting these two things together, we can actually separate out the Hamiltonian, or find the energy as a function of the wave function. We get this nice Hamiltonian that depends only on individual sites. So everything is nice and separated. This is standard Gutzweiler-Ansatz. I just wanted to show it because I did it, and I'm happy. So the question is, what does this 3-body interaction do at the level of mean field theory, right? So here I just, I should point out there's this Z number that shows up everywhere. That's just kind of that's the number of nearest neighbor sites for each system. So in like 1D, that's 2, and 2D square lattice 4, so on and so forth. And largely, we're going to care about 2D square lattices in the future. So when this U3 is 0, not too surprising. We get exactly the normal kind of mod insulator to superfluid phase transition, where we get the insulating lobes for 1 particle occupation, 2, 3, 4, so on and so forth. And we have a second order phase transition from the insulator to the superfluid. All fun and nice. So now I'm going to ask, what happens when we make this 3-body interaction attractive and kind of small? Right? So here it is for U3 equals negative 0.5 times U. And maybe it's not too surprising. I thought it was kind of neat that when we make this 3-body interaction attractive, we make it so that 3-body occupation is enhanced. So this 3-body lobe gets much larger. And simultaneously, the 2-body and the 4-body lobes kind of get shrunk down. Right? So we're just making it so that 2-body, 4-body occupation aren't very favorable, but 3-body occupation becomes quite favorable. Right? You can tune up the 3-body interaction a little bit more, make it more attractive. And interestingly, at a critical value, not surprisingly, U3 equals exactly negative U, the 2-body and 4-body lobes exactly disappear, completely get wiped out. So that was kind of neat. We were happy and we're ready to start publishing papers. But then the next question is, what if we make it more attractive? And so, I thought, what would happen is, OK, we make the 3-body interaction more attractive.
So, maybe it's not the ground state, but I expect that for n equal to 2, we still have a metastable state.
Yeah, there's almost certainly still a metastable state. We're talking all ground state physics here. I'm sure there's a metastable state that would hang around. I don't know how long lived or any of these sort of things. But so this was interesting. So I assumed if we started making this more attractive, what would happen is the 3-body lobe would just continue to grow and grow and grow, and it would start eating up the 1-body lobe, and the 1-body lobe would get, or 1-particle lobe would get smaller and smaller, and the 5-particle lobe would just get smaller and smaller. That's kind of what I assumed would happen, which is why I was ready to call it a day and get published. But then when we decided to check anyway, we found something rather interesting. Instead of just shrinking down the 1-body lobe, the 1-body lobe here actually doesn't change very much at all whatsoever. But what we do find is an overlap between the 3-body insulating lobe and the 1-body insulating lobe, which is kind of weird. Like you could imagine tracing this down, you'd find that if the lobe still existed, it would go down here, and then the 1-body would go up here, and you have this kind of weird region of overlap between the two, which on its own was very odd. And so we decided we needed to focus in on this kind of overlap region. There's another one up here that we won't talk about that much, or I won't talk about anymore, really, right there. So we wanted to focus in on what was happening right there. So if we look at the mean field energy function as a function of the order parameter, right? So here we are in the middle of the mod insulating n equals 1 lobe. That's what this mu value does. You can see that, of course, maybe not surprisingly, this is an insulating state. The order parameter, or the energy, is minimized when the order parameter is 0. Not too big of a surprise. Okay. So then I start turning up the chemical potential, getting closer to this transition point, and we see something kind of interesting. We see that we're starting to develop a double minimum structure in here. So we turn up the chemical potential a little bit more, go exactly to where this phase transition occurs, and we find that it's not a smooth phase transition from 0 psi to finite psi. In fact, this double minimum shows that when you go through this phase transition, all of a sudden you have fully finite order, psi, fully finite order parameter. This is a first order phase transition. It's discontinuous, which was surprising to us because this is just insulator to superfluid behavior. So when we look at the phase diagram kind of close up, this is what we find. We find 3 first order phase transitions, one going directly from insulator to insulator, so we make a jump from n equals 1 to n equals 3, and then 2 going from insulator to superfluid. Further, we also have a triple point, which I find quite cute, in fact, and using some approximations within the mean field picture, we can find exactly where that triple point happens at 0.04 for n equals, for this particular system, for U3 equals negative 3 halves U. And that's all good. But then eventually, if you make J large enough, right, you make it very favorable to start hopping around, the phase transition turns back to second order and goes back to being normal. So this is the phase diagram we've gotten at mean field theory. Yeah.
Did you check the inclusion of quantum fluctuations? Because it could be that this is just an artifact.
That's what we thought. Maybe this is just an artifact. Maybe there's nothing too interesting. So we decided path integral Monte-Carlo was the right thing to do. And that should solve the question, right? Path integral Monte-Carlo should find the exact ground state. And I thought I'd give you a nice summary slide of everything that I understand about path integral Monte-Carlo. So there we go. We go to Barbara and Argivon, and they know what they're doing. And they run a bunch of different checks for us. And this is what they find. So here I'm showing, again, the mean field phase diagram, and then the results from the Monte-Carlo simulations, right? And here black dots are first-order phase transitions they found, and then the open squares are second-order phase transitions. So they're really seeing that it follows pretty nicely with the mean field results, which I was quite gratified to see. And we also found that this kind of survives at finite temperature. When we go to small finite temperature in the Monte-Carlo results, we still see these kind of behaviors. And to really verify that this was first order, right, not some very, very sharp second order phase transition, right, we thought, you know, first order phase transition should exhibit some hysteresis behavior. Right? So in doing the Monte-Carlo simulations, this is actually how Argivon ended up finding the first order phase transitions, just because everything gets shifted and abrupt and is very hard at first order phase transitions. She ended up having to do hysteresis sweeps to find where the phase transition was in general. And so this is what she did. She just, you know, basically in doing the hysteresis sweep, we see that this is the 1 to superfluid phase transition, and this is the 3 to superfluid phase transition. So you can see we definitely see some sort of hysteresis behavior by stability showing up. So this really is saying that this looks like a first order phase transition. Okay. And then we also did hysteresis sweeps for the 1 to 3 phase transition, but it's a really boring hysteresis curve because it's a box. So it's not really nearly as neat as those two. So I'm going to summarize, and I actually did a pretty good job. All right, so just to summarize, I showed that tight confinement, you know, nice optical lattice, really could open up a more efficient wave function overlap and ability to probe Efimov physics. Using this kind of large Rabi frequency that could be there, we can try and use an Efimov state to provide a separately tunable three-body interaction. And this three-body interaction has some surprising and interesting consequences in the Bose-Hubbard phase diagram. And if you're interested, we have this archive paper up and about. And with that, thank you.